we go into our topic, I'm going to introduce the basic concept behind it, which is nuclear fission, fusion, and the hybrid reactor. First, what is nuclear energy? It's the energy stored inside the nucleus of an atom, specifically the strong force that hold protons and neutrons together. When those bonds are broken or formed, that stored energy gets released. First, now, there are two ways to release it, fission and fusion. Fission splits a heavy nucleus into smaller parts. Imagine pulling apart a big Lego tower into pieces, while fusion does the opposite. It forces two light nuclei to smash together and combine into a heavier one. That's how the sun makes energy. Now, there are two. So, what is a hybrid reactor? It's a system where a fusion reaction acts as a helper to drive a fission reaction around it. Fusion produces high-energy neutrons. Those neutrons then trigger and control fission in a surrounding blanket of fuel. This teamwork makes fission safer because you can turn it off by stopping fusion, and it also allows the reactor to burn nuclear waste as fuel instead of creating more waste. So, why it solves real problems? First, the energy crisis. Hybrid reactor could produce massive power using less fuel. So, why? And the second one is nuclear waste. The fusion neutron can actually burn out long-lived radioactive waste from ordinary fusion reactor, which will turn a dangerous problem into fuel. So, in short, fission split, fusion combine, and hybrid use both to solve waste and energy issues. That's the basic concept.
Next, I will be presenting about nuclear fission, which is the process used to generate electricity in nuclear power plants. Nuclear fission occurs when a heavy atomic nucleus such as uranium-235 or plutonium-239 absorbs a neutron. The nucleus becomes unstable and splits into two smaller nuclei. This process releases a large amount of energy in the form of heat, as well as additional neutrons. These materials are called fissile materials because they can easily sustain a nuclear reaction. Nuclear fission is considered one of the most efficient methods of producing energy. Move to the next part. A key feature of nuclear fission is the chain reaction. When a uranium-235 atom splits, it releases 2 or 3 neutrons. These neutrons can then collide with nearby uranium atoms, causing them to split as well. As the process repeats, more energy is produced continuously. In a nuclear reactor, the chain reaction must be carefully controlled. Control rates are used to absorb excess neutrons and prevent the reaction from becoming too rapid. This allows the reactor to operate safely while producing electricity. Furthermore, nuclear fission provides several important advantages. First, it generates a very large amount of energy from a relatively small amount of fuel. Second, it supplies reliable electricity 24 hours a day, regardless of weather conditions. In addition, nuclear power plants produce very low greenhouse gas emissions during operation, making them a cleaner alternative to fossil fuels. These advantages making nuclear energy an important source of power in many countries. However, nuclear fission also has some disadvantages. One major challenge is the production of radioactive waste, which must be stored safely for a long period of time. There is also the risk of serious accident if safety systems fail. In conclusion, nuclear fission is a powerful and reliable source of energy that can help meet growing electricity demands. However, effective safety measures and proper waste management are essential to ensure its long-term sustainability. Thank you for your attention.
Hi everyone, so now we are going to look at the ultimate power source of the universe, which is the nuclear fusion. This is literally the exact same process that powers the sun and the stars, and today we are trying to bring that star powers right here. So what actually happens during fusion? Essentially, we take two super light atomic nuclei and force them together to create a single, heavier and much more stable nucleus. This whole process is driven by Einstein's famous equation E equals to delta mc squared. Now, the trick here is something called mass defect. The final nucleus actually weighs a tiny bit less than the two original pieces we started with. That lost mass is instantly converted into a massive amount of. To make this happen efficiently on Earth, we use the DT reaction, which pairs up two isotopes of hydrogen, deuterium and tritium. Deuterium is awesome because it's abundant and easily extract right from seawater. Tritium, on the other hand, is quite rare, so we actually breed it inside the reactor itself using lithium elements. When these two fuse, they give us the highest energy output at the lowest required temperature. It's not an easy walk in the park. We face huge engineering hurdles. First is the Coulomb barrier. Since nuclei are positively charged, they naturally repel each other like matching magnets. To overcome this, we have to recreate stellar conditions, heating the gas to a mind-blowing of 150 million degrees Celsius to create a plasma state. At this point, a quantum physics phenomenon called quantum tunneling allows the particles to occasionally cheat and pass right through that repulsion barrier. To keep this crazy hot plasma from melting the reactor, we use a giant donut-shaped machine called a tokamak to trap it safely using powerful magnetic field. If we can master this, it truly is the ultimate clean energy. It has inherent safety that offers zero risk of a meltdown because if the machine fails, the plasma goes down and just stops instantly. It's completely eco-friendly with no long-lived radioactive waste, and it's highly efficient by offering 4 million times more energy density than burning traditional coal. That's all from me.
Okay, so now let's discuss about the hybrid reactor concept. So, it is an innovative design that merges fusion and fission technology to reshape how we think about a nuclear energy generation. Okay, to start off, what exactly is hybrid reactor? It is formally known as a fusion-fission hybrid reactor. So the design is centered around a fusion core that is surrounded by a subcritical fission blanket. So let's move on to the mechanism. So the mechanism relies on a process where the fusion core function as an external neutron sources. So the high energy neutron are produced by deuterium, tritium fusion and directed outward into the fission blanket. This neutron also then force the fusion material to split, which in turn generate. Let's move on to the advantages of hybrid reactor. So what is the primary advantages of hybrid reactor? Of course, it is about safety, right? Because the fission blanket is subcritical, it does not contain enough material to sustain a chain reaction on its own. If the fusion core is turned off, the fission process stops instantly, resulting in zero risk of a meltdown. The next advantages of hybrid reactor is definitely fuel flexibility. Why? Because it provide flexibility by allowing the use of non-fissile fuels like thorium-232. It also has the capability to transmute or burn up dangerous nuclear waste produced by older fission reactors. Finally, this is our flow system for hybrid nuclear reactor. So this flow system is designed for practical energy conversion. A central plasma ring or tokamak acts as the neutron generator. It's sending energy into a jacket of heavy metal fuel rods. This heat is then processed through a standard steam turbine cooling loop to generate electricity. That's all from my part. Let's move on to application and future potential that will be presented by AFIQ MUAZZAM. Let's go.
Okay, moving on to my part. Let's take a look at the practical applications of nuclear hybrid system. When we talk about applications, we are looking at two major areas, which is future clean energy grids right here on Earth and deep space rocket propulsion. For the first applications is future clean energy grids. Grids modernizations deployment in future clean energy grids to meet rising global electricity demand.
Next up, deep space rocket propulsion. Deep space rocket propulsion utilizing high energy density for next generation along space distance, space explorations. Right now, pure commercial fusion technology is still years away from being fully mature. So think of this hybrid system as a crucial transitional bridge. It allows us to generate massive power now while the technology for pure fusion continue to develop.
Now, let's address a major concerns. which is safety issues up. Yes, this system is significantly safer than standard fission reactor. However, we have to be realistic. It still deals with the radioactive activations of reactor materials. But here is the brilliant part of the technology. It actually helps with existing waste management. By technically burning high-level waste taken from older legacy reactors, it can drastically reduce its radioactive lifespans. We are talking about shrinking a lifespan of hundreds of thousands of years down to just a few centuries. That makes waste management incredibly more manageable. This brings us to its future potential, which is my last context for this video presentation. This technology provides a highly realistic path to abundant carbon-free energy. And unlike solar or wind power, which require massive amount of real estate and land area, hybrid system can combat global climate change with a very small physical footprint. So, in conclusions, nuclear hybrid system elegantly bridge the gap between our current fission's capabilities and our ultimate energy dream of fusions. It provides a safer, cleaner, and virtually inaccessible power sources for the future.
So that's all from us. Thank you and bye bye.